Here we go. Huh? I guess 3 weeks left? 3 weeks left. Isn't that cool? Crazy. I'm not going to get through as much stuff as I was hoping in this class. I decided that this weekend. I was looking through over some things, but it doesn't stop me from having enjoyment in making the homework assignments. So I just posted another homework assignment, which I'm fucking stoked about. It's sick. All right, it's long. All right, hopefully it's difficult. I basically built a model and then I messed it all up, and you guys have to go through and fix it. Okay? All right, and so you're going to use all the stuff we're going to talk about this week. It's due on Monday, a week from today. Okay, I'll pull it up here in a second so everyone can be on the same page, because I know that can be a bit of a pain sometimes. All right. Homework 6 though first, handing it back. Everyone did very well. It was very, very simple, right? Hopefully it was just trying to get your toes wet a little bit. Talk about loading, talk about orientation, maybe do a little bit of model description. Okay, I'd say for the most part everyone was on the, I wouldn't say the most part, but definitely there were some lighter descriptions than others. I didn't take off for that. The big things that I was looking for here that weren't there sometimes was this idea of when you calculate deflections, what type of loads do you utilize? What's that? Service level. What does it mean to be service level? It's not factored, right? When you say not factored, what does that mean for like earthquake or wind? Factored. Right? You can tell that that's not necessarily the best way to describe it, right? What we want is a load with which we are actually expecting to see, right, in a design level event. Okay? Wind load's interesting because when they do service level for wind, right, we multiply it. What's the factor we put on it when we do wind loads at service level? 0.6. Service level, 0.6. Because we calculate wind at strength level. There's a big change when we went from the ASCE 705 to ASCE 710. We made this jump and they decided, okay, well, we're already calculating earthquake loads at strength level. We're going to calculate wind loads at strength level to give a better kind of comparison between the two, right? There's a lot of probability and statistics buried in all of that, but that's what they decided to do. So when we calculate deflections for those two things, we do 0.6 for wind. What do we do for earthquakes? 0.7, right? And that's the intent there is to reduce it to what we're actually going to see, right? Back to ASD, I would call it ASD, or allowable stress load combinations, where we're not trying to increase the demands, right, and decrease capacity, which we do with LRFD, right? We're manipulating both sides of the equation with LRFD. For ASD, we're just manipulating the capacity side. You have an allowable stress. For how many of you took wood? Right? So you did ASD for wood design, right? Masonry, ASD for masonry design, right? And in all of those, you're calculating a demand based on ASD combinations, relate that back to an allowable stress. Not as efficient or as accurate in some instances as the LRFD method, but it's still commonly practiced in those two materials, masonry, wood. Maybe someday like in the NDS, there was, I don't know if, did Damon teach wood? So did he talk about, there's LRFD in wood that you can utilize. Similarly, in the steel manual, it does everything twice. It does ASD and LRFD. Because there's a lot of holdouts out there, just like their ASD. Right? Yeah, so that was one thing, is making sure you use service level demands when you're calculating deflections. Right? The other one was, when I asked for you, it says, if there were concerns, explain how you could address them in your VA analysis. I expected something more than just saying, I'm going to check a box that says PW, right? You know more than that, and I expect you to know more than that. Give me something, right? And most of you did give me something. Some things were not as accurate as others, but some description as, okay, if I do check this box in VA, right, what is VA doing? What is VA doing?
It goes through iterations, right? Like
it does not go through iterations. No, it doesn't go through iterations. We talked about that. There are massive problems with trying to program that, right? Remember that?
It does the geometric.
It does the geometric stiffness matrix, which is doing What's it taking into account? Deflected shape, right? So it's saying, okay, instead of going through like a lot of you did by hand and you said, okay, I'm calculating P delta, this is the first iteration in the hand method, right? You calculate P delta, then you'd apply that moment, and then calculate it again, and then calculate it again. At some point you're gonna converge, right? Well, in visual analysis, it says, okay, we're not gonna do the iteration. What we're gonna do is, every time that that node is moving over, we're gonna adjust the stiffness, and that stiffness is going to incorporate the fact that we're gonna have P delta effects happening. And it essentially affects the strain energy that's going into the system. And we talked about that, we went through the derivation. So that's how VA is doing. I wanted something, a method, some mention of that's what's going on, right? It's taking that into account. If you did say iteration, that's not right. It does not do that, okay? Which is fine. That's why there's homeworks, okay? So that was the two big ones. So what did we do? Well, I wanted you to do an analysis. This was my little model description, right? Some discussion on what's the loading all about? What's the orientation of this thing all about? What are the nodes? What do they look like? Are we doing one element? Are we doing two elements? Or what kind of fixity do we have? What are the coordinate system, right? What's the material? Okay, things like that. That's what I was looking for. Then we went through and I said, all right, I'm gonna do a check by hand to make sure VA was good. I think everyone got this. It's all statics-based stuff, right? Where we would calculate the axial load, moment, and shear based on the governing load cases. All right. If you had a decent description of why you would ignore self-weight, I let that go. Most of you did not, okay? Why ignore it, right? It's there, it's real. If you were designing a building, right, self-weight is there. Right? We did talk about the modal analysis method. I mean, we ignore some self-weight stuff. And there are areas where you would. If you explained that, okay, that I ignored it because, say, maybe it was 1% of the overall applied loads, right? If you just said I ignored it because it's a more accurate model, that is not right, right? The most accurate model would be incorporating the self-weight of a member. So you just want to make sure that, you know, if it's there, account for it. I didn't tell you to ignore it. I didn't tell you to include it, but I wanted you to model this column that's sitting over there in Langford. And if you did it on your own for Hicks, for TD&H, for whoever else, right, I would assume that you would apply the self-weight to it, okay? Unless there was some reason not to. And you would say that in your calculations, okay? So make sure you're documenting. Again, this is the deflection, service level, 0.6. And then I just classified my model results, right? One thing to note in here, and it just takes time when you're running a program, is you can have it give you just the extreme values. Right? You don't need to give every load case, load case value for every node sort of thing, right? You can click on this and in VA you can say, all right, I want the extreme values only, and it's going to shrink this down and only give you the rows that give you the extreme values for each one of these columns, right? These are all the highlighted ones. Most of you got that, but I was just saying in the future, okay, there's helpful stuff. It just takes time, okay? But if you click on it, you can, on the left-hand side, manipulate that table and you can just do extreme values, right? So we did that. Second order effects of the concern. Well, some of you guys did this differently as opposed to like including the self-weight value, but overall, right, VA does it, and it did it non-iteratively because when it is pushing that member over, right, the stiffness it gave the member was a function of the deflected shape of that member. So as it moved over, it changed the stiffness, and so it was essentially doing the iteration in one step. Right? And so it ended up getting, I think everyone got very, very close. I said I would not share my colleagues' concerns, okay? Something to note when you're doing the homework, just making sure that you're answering all of the questions, right? I full-heartedly know that a lot of you know how to do P delta analysis, but I asked you, okay, well, is it a concern, right? You could give me all this stuff, right? But I really said, okay, if John came to you and said, man, I'm really freaked out about this P delta analysis on this column, I want you to say, well, John's probably overreacting, right? Or Elias is overreacting, okay?
For that deflection at the middle where you applied self-weight,
I just assumed it was a straight line,
you just halved it?
just to make sure that it was somewhat incorporated so that I would get somewhat closer. I mean, I calculated.
You would ideally use like the shape function, though, right? Like,
you would be
Which
looking.
is linear.
Yeah, well, the way VA would be doing it is it would be doing its energy equivalent forces, right, and be putting those forces out there at the nodes.
Right.
So it would take half the load and put it all the way out there.
Yeah, so have that self-weight already up there.
Yeah. So that's why I was really, really close, is because I took the full self-weight and I was halfway out there.
Yeah.
So I said, based on the magnitude of increased demand, I would say considering P delta is not required. I think a lot of you saw that, right? This is where engineering judgment comes into play. It's like, okay, some of you also went a step further and related it to the actual capacity of the column, whether it was in VA or went through the steel manual, right? And saying, okay, does this make sense? Some of you went through and looked at a very unique approach would be to look at the seismic requirements, right? And there's a stability factor, theta, okay? And you could go through and you could really relate this back to it, right? Just saying that this wind load is now a seismic load and figuring out whether or not you needed to consider P delta, which is a check in chapter 12 in ASCE 7, but it only really relates to seismic loads, but another good gut check, okay? But I would also, I put this caveat in here is because, you know, as we were relating P delta, we were really just relating back to the magnitude and how it related to the demands on this column. But sometimes there are things outside, right, that are requirements like that seismic check, right, stability requirement. There's also IBC deflection requirements, right? Also in AISC 341, story, drifts, all sorts of other things, right? So just relating it back to strength in some scenarios, right, might not necessarily deem it like inapplicable. Right? It does increase the demand by 1.1%, okay? But in some areas it might not be as easy, right? It might not be as small of an effect as it might be if we were looking at deflections and we were like right on the edge of the tolerance, which ends up happening a lot of times when we're looking at flexurally dominated lateral systems like cantilever columns or moment frames, right? A lot of times they're really strong as hell, right? The strength is not a big issue, but it's the displacements that really govern what the design is, okay? But I said I didn't care.
Displacements because of P delta or because of like serviceability?
Serviceability usually, yep. But it can also then play a role in P delta. And that's why that check is in the seismic, like in the stability factor, theta, is in the seismic code, right? In ASCE 7, they're taking it a step further and saying, okay, when you go non-plastic, like when you go plastic, right, and you start incorporating, I don't know if you guys remember the CD value, which essentially relates to the fact that we're doing an elastic analysis, but in real life, this thing is going to be a plastic hinge, so it's really going to displace a lot more, right? It takes into account some of those effects and makes you limit your displacements associated with that. So. Right. If I use VA, I would implement second order analysis where geometric stiffness is created that incorporates the equilibrium of the deflected element. Something along those lines, right? Because that's what VA is doing. All right. So that is homework 6. This is my new homework I'm so proud of, okay? This is the connector, the stairway elevator connector piece that takes Norm into the parking garage, all right? I gave you structure information, right? Floor loading, dead load, 60 pounds per square foot. This is a 5-inch concrete on metal deck. It spans north-south. The live load is 100 pounds per square foot because it's egress, right? You get that out of ASCE 7. Roof loading, we have 15 pounds per square foot. It's got 18 gauge metal deck. Okay, that's that picture up in the right there, okay? Metal deck, this is actually pictures in there. Got to spend a little bit of Easter inside this thing, okay? Dead load is 15 pounds per square foot. It also spans north-south. The snow load's 40 pounds per square foot. Okay, that's roof snow load, right? That's dictated by the city of Bozeman. Lateral loading, well, we have a wind load, okay? Strength level, 30 pounds per square foot. This is projected on the windward side of this stair tower. Ignore the parking garage, right? I'm simplifying this. When you go out there, I give you a VA file. It's out there, and you'll see I just modeled this, okay? All right. North-south earthquake, well, I gave you story forces, right? How much load needs to be put at each one of the floor levels from first up to the roof. Lateral systems, okay? or I guess, wow, we jumped way down there. Yeah, lateral system, sorry. East-west direction, we have steel special moment frames. North-south, we have steel special concentric brace frames. You can see the moment frames. You go walk in here, and there's a little extra credit here that's going to ask you to go walk over there, okay? You can see the moment frames. They're really easy to see. This is a moment frame connection. It's a RBS connection type. Maybe you guys learned about this in steel yet? No? Talked about it, where it's a reduced beam section, right? So we've basically cut out portions of the top and bottom flange to weaken this member right here. So when this thing gets pushed over in the east-west direction by wind or earthquake, this thing's supposed to go completely plastic. It's supposed to just bend, right? Turn into putty, right? A lot of energy dissipation. And we want it out there, so we then reduce the strength of the beam out there. So we have moment frames at each of the east-west frames. So in the VA model, we have a frame. I put in frames, right? So each one of them in the east-west direction. And then last bay, right? The brace frames are at the north end bays only. So out here, you can't see them. Obviously, they hit them. They're where the elevator are. Here in the elevator, both sides of you are special concentric brace frames down the whole height. Okay. Framing, well, I give you what the framing should be. W16 by 57 columns, 12 by 45 moment frame beams. What's that?
Should be.
Well, I mean, I changed a lot of shit in there. Yeah, I can't keep track of all of it, right? So you're gonna need to look at this to do this. I like kept going. I'm like, damn, I better stop because I like. Yeah. So W12 by 45 moment frame beams. I gave you the joist size and the beams that you should have for the brace frames. If it's acts as a girder, I've got a W14 by 30 girders. HSS 3 by 3 by quarter braces. All right. Materials. Okay, I didn't mention it here, but you should go to the steel manual. All of you have a steel manual, right? Tell me if you know. Everyone has a steel manual. Okay, love it, right? Favorite book in the world. Right? In the steel manual, if you learn, I know if you took a 315 from me, which none of you did, you go through, there's a little part in there that gives you the preferred material specification for each of these, right? What's W's sections? Okay, what are HSS members?
36K.
No, what? No!
45.
48 or 50.
No, it's moved up. It moved up. It's 50 now.
Yeah.
It's A500 grade C. It used to be A500 grade B. Okay? Which was 46, now it's 50. All right, that's the preferred specification, okay? So think about that, right? Those are some things I could change in this model pretty easily. Connections, so at the moment frames, we have fully restrained at the moment frames. Pin brace frames, pin shear tabs, those are all of our gravity connections. What else? What are we at now? Layout, so it's 15 feet wide, it's 40 feet long. We have a 10-foot brace frame bay at the end of our building. The moment frames, well, we have a frame at 0 feet, 15 feet, 30 feet, and 40 feet, right? So 30 to 40, obviously that's where our brace frame bay is, 'cause it's sitting between these two frames in that end of our building. We have 15-foot story heights. We want to ignore, okay, I did not model, and I don't expect you to assume that that's what I wanted you to model, is the stair landings, or look at combined orthogonal lateral loading, right? Don't worry about the fact that you need to look at wind in like 75% in one direction, 75% in the other direction, okay? Don't worry about that contribution. The other one is seismic, right? If you have a common element between two, you have a, combined. Anyway, if you have a brace frame and a moment frame that share a column, right, in two orthogonal directions, you technically, based on the code, need to give it 100% in one direction, 30% in the other direction, right? Don't worry about that, okay? Don't worry about the combined, just look at this loading in the two directions, okay? Now, here comes the good part, right? Your colleague Tim decided to quit your company. Now your supervisor has asked you to pick up the modeling effort. Tim didn't leave you with any information on the modeler's approach. What an asshole, right? Tim's model is on D2L, so it's out there under the homework file, okay? And currently does not run. That sucks, okay? The intent of this model will be to design the moment frames and brace frame members and foundations, okay? So that's the intent of this model. So if you were designing this, that's what you should be taking into consideration when you are manipulating this, making sure things are right, changing stuff, right? The intent is to look at the frames, and brace frame, the moment frames, and then the, foundations, right? So you want to know reactions, okay? So what do I ask you to do? I complete the following: review and adjust the model's boundary conditions, loading and elements, document all adjustments made, and provide a model description as discussed in class about your final model, okay? When it comes to the model description, right, there is no such thing as going too far, okay? Be concise, especially in this homework. Like, I need you to keep track of what you changed in this model, right? So be methodical about this. If you moved a node over 2 feet, tell me what node you moved over 2 feet, okay? Something of those sorts, right? Once you've done this, I want you to use hand calculations and verify the following results from your VA model using surface level loads. Okay? So what's the global horizontal earthquake and wind reactions? Right? What are the global vertical dead load, live load, and snow load reactions? Okay? The wind second story shear, or the second floor story shear. Okay? I want to see how much load is coming in at that second story due to wind, due to surface level loads, right? You confirm that, right? You know how much load's going into it. You know the windward pressure on this building, right? You could then, based on the results you can pull out of VA, you could get, okay, how much load is going in at that story? And you need to confirm that with hand calculations, okay? Third, without your knowledge, your supervisor conducted their own finite element analysis, manipulating Tim's original model, and came up with the maximum envelope LRFD reactions at the base of the northeast corner column of the following, right? Northeast, so that's the one underneath the elevated walkway right there in the corner. And that your supervisor, gave you these reactions. So the reactions at that node at the base is going to be plus or minus, this is what they got. Okay? Do you agree with their values? Why or why not? If you were to compare your models, what would be your first model parameter you would compare and where? Right? So you say, okay, this is what I got. Well, shit, this is what I got. These are different. If you opened up these two models, what would you look at, right? What would you look at to compare these to see, okay, something's different, right? What's a parameter that you would use, and where would you say, look at that parameter? Right? Extra credit. Walk over to the stair tower and tell me why this special connection was used. There's a connection in there. It's used pretty prevalently throughout the stair tower, okay? I want you to tell me why this special connection was used. What boundary conditions would you impose in your model to represent this connection and why? And you will need to include a selfie in front of this connection, okay, for extra credit.
Can you tell us what it's called?
It doesn't have a name. It's custom. Yeah. We made this for a specific purpose. I detailed that for a specific purpose, yeah. Whether or not it's right, I don't know. But I'm curious how you guys looking at this and walking over there and looking at how it's used throughout the thing. Because you can see a lot of these connections sitting out in front of along the stairwell, right? And so I'm curious what your guys' thoughts are.
How many extra credit points?
You'll have to wait and see.
Already.
I don't know. If 2 of you do it, probably a lot more than if the whole class does it.
For the second part,
Yeah.
is that just like one move, like reactions of one move, or like all of them?
This is global, so looking at total horizontal earthquake and wind reactions.
Total vertical dead load.
Because it'd be really tough. To say decide what the reaction is at some of the moment frames, right? Because when you have a model this size and you have loads coming in from all of these levels, everything is distributed based on stiffness. So, I mean, you could hand calc what you think it would be at, say, 1 moment frame bay, but that might not necessarily be really close to what VA shows, especially if you have rigid diaphragms in there and things that are distributing stuff, right? It can kind of manipulate what the individual reactions are, but if you looked at global forces that are acting on the entire model and you looked at global reactions, you should be able to make a comparison and say, okay, have I applied enough load to this model so that the applied load matches what the loading requirements were? Does that make sense? That makes sense. Any other questions?
You want us to change your model, or can we start with
Change your model. Change my model. And I didn't say this here, I'm gonna put up a submission box to put that model, send that model to
I have unrelated questions, they're VA related.
me. Okay.
How do you offset, like you're talking about offsetting decks,
Yeah.
index? Where is the button for that? And can you do it with areas or does it have to be plate?
It has to be, well, you can offset any member.
Is that in
And
the
so,
model view?
yes, when you click on the actual member itself, you can do an offset and you can drop that member. And you can say, put nodes at top of member, and then it will
Oh,
move
okay.
that beam so that it's down there. And if you look in the help file, the way that they do that is with rigid links. And they end up saying, okay, now I'm gonna put a series of vertical. So glad you joined us today, Aaron.
It's been a while since I've been here on Monday.
It sure has, yep, it sure has. Right, so we've got this concrete on steel beam, and so this is the real world. Well, in VA, it does something like this, where we're just gonna overlap them two together. Right, so now we have a node here and a node here. So what does VA do? Well, it says, okay, if we keep the node, say up here, they do a series of rigid links. So this might be the rest of the model might, continue off from this point. But what does that do? Well, then it starts messing with the stiffness of the entire member. If you go in the help file, they talk a lot about what that does. And it's gonna change the moment.
If you have a plate with like a column framing into the plate, does the plate, or does VA like analyze the column as if it's like stuck into the plate, and so it's got a slightly reduced overall column height? Or does it still do node to node?
Node to node, that's all it ever knows,
Okay.
is node to node.
And then when
Do
you
you
have
have like a
inclined,
little question thing
I
here?
have a question thing. I have a little, when you have an inclined plate,
Yeah.
how do you get it to not load normal to the surface? Like if you wanna get it to load just with the Y direction versus like, let's say I play at 15 degrees, instead of having it load directly normal, can you load it like directly down?
It doesn't give you the option to just load in the global direction, the pressure? I'm pretty sure you
The
can.
way I did it was with areas, and I generated plates based on the area, and then it literally only gave me the option to do a uniform pressure. It was
Over
only
the,
normal to it.
I thought you can do like, it says you can do local axes or global.
yeah, you might
direction.
look and see and make sure that the axes over which you load it were, instead of the
It was
little
like,
z.
I feel like I saw that box, but it was like grayed out, like it wasn't an option to change.
I'm not sure.
I don't
I'd have to
know.
open
Okay.
it up. We can talk more after this, though. I'd be interested. Okay. Any other questions? Maybe related to the homework? Huh?
Not yet.
Okay, cool.
Wait, is the little connector tower thing part of it? The elevated-
No, ignore that.
It's just a box?
Yep. Yep. I would say that in manipulating this, every. No.
So another
I would,
question.
like stairs, landings, the bridge, okay, the parking garage, like ignore all of those things. We're just looking at a tower. So that means like, when you're talking about wind loading, when I said the windward side, what does the windward side mean?
Side the window.
Sides the wind's hitting. So you're gonna want to, in all four directions, right, make sure that we're loading it on the side that the wind is coming from, right? Yes, sir.
So in Damon's class, we accounted for accidental eccentricities with like a total offset in your nodes in the model, like offsetting them to. I'm not saying
Don't worry
it's the right
about
way to do it.
accidental eccentricity.
Okay.
Don't worry about that. Okay.
You just said on the windward side, so load every side with the wind.
So I gave you a wind load that was a pressure based on the windward side loading.
Yeah.
So when you're in wind loading, usually depending on what chapter you use and you're developing those loads, you will get a leeward and windward pressure that you would apply to your building. I'm just saying that you only have a windward pressure. And so when you're looking at wind coming from the east, right, hitting this broadside against that deal, you've got 30 PSI. And if you're looking at it from the north, 30 PSI.
So
West, south, same thing. Yes, it's all four sides. Ignore that the parking garage is there. We're simplifying this, right? We're simplifying this.
You need to calculate leeward pressures too?
Nope. I gave you all the loads that you need to apply, right? And use the fact that you are looking at what are the forces, or you're gonna be designing the brace frames and the moment frames, right? As your key. You're not worried about designing the joists, you're not worried about designing the girders, you're not worried about designing the roof deck or the floor deck in front of the elevators, like any of that stuff, right? Okay.
Do you want a certain way to load, like, actually, never mind.
That's where like description is key here, right? So if you change something, right, or you think something's wrong, or you add something to the model, describe what you did and why you did it. Right? That's what the tough part of this class is, like, we are getting so into the fact that it is up to you, right? I can't tell you what is right and wrong. There are some pretty good, I don't know, guardrails associated with, you know, doing something wrong, but there's a lot of space between the guardrails, right? We're on a big freeway and there's a lot of opportunity there, okay? You can do a lot, right? As long as you think it through, right? Be methodical, think about what you're doing, why you're doing it, right? With the intent of, I'm designing this moment frame. Well, if I'm designing this moment frame, this load I feel like can be placed here or should be placed here, or the fact that it might distribute differently if I place it here would be a good idea, right? All of those things. Just document.
But the model description is not just based on our changes, right? It's like, is it based on the whole thing, like pretending like we started from
Yes.
scratch and like
Yep.
we had
So
all
it's like
these
you
things.
get to the end
So
and
you
you're
need to
saying,
describe, like,
I
elements
feel-
that were already there that are right. You have to describe that.
well, so like,
right?
I want you to describe how you're getting to that point, right? To your final model with which you feel comfortable about the results that you're getting, right? So that's, I want you to describe that step of how you take Tim's model and you make it your model. And once it's your model, I want you to provide a model description saying, okay, hey, if someone were to look in my calculations, right, ignoring the fact that I took someone else's garbage model and I made it my own. Now that it's my own, I'm gonna explain, hey, this is this, this is this, this is why this is there. So in some cases, you might be needing to explain loads on that model that you never changed,
Right.
right? It might be right, I may have done something that you agreed with in the loading of, say, the joists, right? Please, someone go and open it after this class fairly soon to make sure that it opens and, like, you know, there's no issues. I didn't use any areas, everything is just plates and members and nodes, okay? And so I want to make sure that functionality-wise, because there's some limits to the educational version, and that's why I picked this and not doing like Miller Dining Hall or something like that, right? Because there's limits on the amount of members that we could use, right? And nodes and plates. Just wait for your final, then it's gonna get fun. So stoked for this.
So no more homework, so you just.
No,
You're
yeah,
gonna
there's
spend
gonna be,
all
there's
that-
at least one
you're
homework
gonna
to
spend
left.
all that time working on the finals.
Yeah, that's fine. It's fine. Maybe we'll just have a group oral exam around the campfire, bonfire. Then we'll really know what you know or don't know, or what I know and don't know. Right? So- okay, here we go. What did we talk about last week on Wednesday? Well, we started talking about boundary conditions, right? This is gonna be critical for this homework assignment, right? Overall, we're using it to constrain or release the model, right? And we're doing that to, as best we can, match this model to our mathematical model, which was our simplification from the real world. Okay, I feel like I'm beating a dead horse here, but that is the root of what we're doing, right? We make a bunch of simplifications, we make these two big jumps, okay, from the real world, mathematical, now our model. And we want to make sure that the behavior matches as close as possible to that mathematical model. And we do that through connections and supports and members, loading, all of those things. Okay? So when we look at boundary conditions, I'd say it's a major source of error or instability in our modeling, is fucking up the boundary condition. I can tell you, I messed up a lot of boundary conditions in that model. Okay? Okay? It's not hard to do. It's really easy to do. It can be one node, right? It can be 20 nodes. Okay? It can be one member. Right? Stiffness attracts load, as we talked about. Right? Depending on how you load the model, that load may distribute differently. That may or may not be of interest to you based on the fact that you're looking at designing, say, the foundation versus designing one of the joists in our, in the grander scale like on the third floor, right, landing of that elevator core, right? So with stiffness attracting load, over-constraining the problem can result in inaccurate load path. Releasing too many degrees of freedom can lead to instability or inaccurate load path, right? A lot of opportunities for inaccurate load path. And we talked about whether or not you fix the ends of a member obviously is going to change, right? Versus going to a simply supported beam, versus now you provide this inability to provide, run axial forces. So if you put axial load in here, right, it's going to transfer differently. And here it's going to stop. If you came on the right side, it's going to stop here versus traveling all the way through the member. Pin, right? If we just pin the ends of our member, well, we don't end up having a way to fix the torsional, right, rotation of this member, so we can have instability by not fixing it enough. Well, how do we implement this? At our nodes, well, the nodes all default to free, right? This is the support frame in VA. So what we end up doing is not using a highlighter. We want to restrain our degrees of freedom. This gives us support, right? In this case, it's displacement based, right? Whether it's a translation or a rotation, we can fix those. If we do fix those, though, what does that do? How stiff are these? Infinitely stiff, right? It is not moving at all. How accurate is that?
Inaccurate.
Depends on what you're looking at though, right? It might be inaccurate if you were looking at designing, say, a pile, right, where stiffness can be a huge contributor to the overall performance of that pile, right, or the pile cap or the foundation element, right, a footing, okay? So we can impose in some instances a support that isn't infinitely stiff. Oops. Essentially a spring. And those springs we can do with respect to displacement. Or rotation. So in VA, we can generate what's called spring supports. We can decide on the node over which it's acting. Okay, that's great.
I have a question for the homework again.
Yeah.
Do you say what the foundation situation is? Like, is everything pinned? Is everything fixed? Do we have to figure that out?
You have to figure that out based on the lateral system, and I guess overall, just think about the fact that the intent of the model is to design the brace frames, the moment frames, and some foundations. Okay? Right? And based on the information that I give you, okay? I mean, when we talk about this, right, generating spring supports, in order to generate spring supports, a lot of times we need a stiffness for these soils, right? Okay? I didn't give you any stiffness. Okay? I guess if you wanted to, go look up some stiffness based on some general soil properties, right?
But you're not asking for that.
Not asking for you to do that, but I'm asking for you to impress me, Elias. That's what I'm asking you to do, right?
Well, we won't get
Oh God, doc for it? Is that where you're
all
going?
of it pinned.
Oh my God.
All of it pinned, which is a fair assumption depending on how you
It can be a
put
fair
it
assumption,
straight.
yep. If you wanna pin it, you wanna fix it,
That
whatever you wanna do,
doesn't matter, as long
just,
as we explain it.
yes, explain it. Explain it. And we're getting in this weird world, I know, it's weird, right? Damon's class, it's always like there's a right answer or a wrong answer, right? This is. What?
I mean, it's surprised.
I've never gotten a firm answer, David.
Shit.
After many years.
Oh, man, damn it. Okay, well, generally, right, in design, there's some very strict guidelines, and that your ability to manipulate what you use to design something or what's right and wrong is harder for steel than it is for getting the loads in the first place, right? ASCE 7 tells us, if we're looking at an exitway, it's 100 pounds per square foot. Can't really get around that, right? But now you're like, okay, I gotta take that loading and I need to figure out what the reaction is at the base of this building, and there's a big gap, right? If you go into the code, maybe I should bring it up when it talks about modeling and actually analysis. It says you can use a three-dimensional element model that takes into account mechanics and material properties, right? That's all that VA does. It doesn't really tell you like you do this for this type of foundation, or you do this for this type of brace frame, or this moment frame, right? It's super open, and that's where you got to explain yourself. Right? I'm saying, okay, I did this because I think this is, the right path because of this, and this. Okay.
Let's look at live load reduction as well.
What's that? VA can incorporate that, yeah. And if you want to incorporate that in that model, it may or may not already be incorporated, right? It's up to you. Okay. But if you do incorporate it, tell me why, or why or why not you would want to incorporate that. Okay. Live load reduction, yeah, beautiful, right? I'll tell you, yeah, I'm not going to help anymore. Okay, generate spring supports. So what can we do? We can do displacement or rotation, right? The type, action, normal, two-way. Well, that means that it works in both directions, right? You pull on it, you get a force. You push on it, you get a force. Well, you can change it so it's compression or tension. All right. D or R. One way. Two-way. What is one element that we might design that we would want to look at? One-way displacement-based springs. What do we design as structural engineers that you can push on it and it gives us stiffness, but if you pulled on it, it wouldn't be able to pull back? What's that? Foundations. Exactly. Footings, right? You can push on them, they're going to push back, but if you lift that footing up, it's not going to hold you down, right? So in this case, you could say soil interaction a lot of times. What is a foundation element that's two-way?
Base plates,
Pile.
anchor bolts, piles.
With respect to like in the dirt.
Piles.
Piles, yeah, or helical piers, same thing. Piles are also interesting because you might want to put a rotational spring there, right? If you guys have taken geotechnical structures, okay, but you put this pile in the ground, right? There's friction associated with how that pile how you can or cannot pull the pile out of the ground or push it into the ground, right? So that's two-way action. Well, that pile is also looked at. If you were to push on it laterally, well, that pile can rotate, right? There's stiffness associated with that rotation, so you might want to put a rotational spring on the bottom of your structure. There's things in ASCE 7 which allow you to incorporate soil interaction, and there's some guidelines associated with what you need to consider and what you don't need to consider. That I've never, other than doing like the springs on the bottom of a spread footing, okay, I have never incorporated the soil beyond that, right? It'd be one-way action. And if it's a helical pier, I just assume that helical pier is stiff enough that it's just a pin. Yes.
Do you find that the helical piers are governed more by lateral versus like the allowable that you have to do when you're setting them up?
It depends on.
Because they don't give you a lot of language usually on the lateral, like
Well, you just batter.
soil specific.
Well, you batter the pile, right? So, like, instead of putting the pile straight down, then you can drill the pile at like a 45-degree angle,
Okay.
right? So you still get the same
So you've
like load characteristics of that pile. You're actually loading the pile in and out, but that obviously has a component in the lateral direction.
You're not talking just like all of them directly drilled down.
They
There's
do
still
have
some
some of that, but
resistance.
then I would say that it gets for very small loads, I would probably feel comfortable with just doing that, right? And looking at maybe the cantilevering some of those, the posts of the helical piers. But for, like, you're talking helical piers, right, or piles?
Yeah,
Helical piers, right? For helical piers, you just start drilling at an angle. Have you seen that before, son? You've done
Yeah,
that?
you do tie back, cause they're such slender elements, you
Yeah.
know, if you need like actual lateral resistance, you have to batter them for it.
So you just put them at it. But if
If
you
you
were
got a
like,
house sitting on helical piers, how do you cast in, I guess you could with tiebacks. If you've got like not heavily loaded house with 200 helical piers over a 5,000 square foot house,
yeah?
I mean, that little bit of lateral cantilever resistance adds up.
Oh, for sure, and that's what, I mean, if you felt comfortable with doing it, the thing is like, when you look at that helical pier sitting in the top of the soil, right? The top foot of soil really isn't going to, it's like you take a fence post and you push on it, right? And that fence post in the ground, the top like 6 inches of the dirt really easily starts pushing away, right?
Yeah.
And your real lateral resistance is down deeper in the soil. And so, I mean, if you could be conservative about, all right, I'm gonna cantilever it maybe the first 2 feet, right, below the footing, and say that that first part of soil isn't gonna do shit for me, and then I'm gonna look at just the strength of the helical pier, that would make me personally feel better about it, and if you were okay, then maybe you'd say, all right, I'm not gonna batter any piles. But to batter a helical pier is really not that hard. I mean, if they're putting in, 500 of these underneath this, house, right? I mean, those helical piers have a lot of strength associated with them, right? And if you put them in a few strategic locations that were battered, you'd probably get the lateral load out of that. Because they literally just like start screwing and then they lay it over and then they screw it into the ground.
Is that what, is batter just being at an angle?
Yes. Yep, battered would be it. It's pile talk.
Aren't-
Pile
I
time.
understand.
Yeah.
Helical are easier to put in, but driven are much stronger.
Yeah, driven, I mean, normally, I guess I've seen battered piles in like railroad bridges and stuff where you have big bends. But like for I guess what would be one of them? Well, the Gaines 101, the new Gaines 101 thing, those were all vertical piles. And then you get to like drilled piers where they actually like drill down 30 feet and they have like a 4-foot diameter hole that's 30 feet deep, and then they put a rebar cage, and then they fill it with concrete, like college business is sitting on those. You're not necessarily gonna wanna batter a rebar, like how do you do that? So then you end up you get a geotech that comes in and says, okay, your lateral resistance of these piles is this, and this would be your stiffness, right? So you end up getting a consultant in that gives you more of that information.
I think just like helical was mentioned only when like you can't do the other ones, like it's softer on the soil and you're not like vibrating the buildings around it and stuff by using like.
Yeah, I mean, they're
pile.
becoming more and more common,
There-
for sure.
There's reasons to use it, the other ones are just stronger.
Yeah, I
Those
mean, and
ones
they're
are just-
cheaper too,
Yeah.
because like, I mean, out in Three Forks, I don't know if that's where the house is at.
No, it's an item.
Like, if you drive to Helena and you get off of Weed, Montana, and you head on 287, all the houses on the west side of the highway there are on helical piers.
It's a shit place, isn't it?
Yeah, there's bentonite, and so what it ends, it's expansive soil. So if it gets wet, there's a layer underneath the ground. It's like 30 feet deep. So you can either over excavate and get rid of all of that, right, and then build back up, super expensive, or you just put your house on stilts, right? And so that's what the helicals do. So all of those houses are generally on stilts.
You're talking helicals with like void forms, so that it's legitimately just sitting on them.
Usually that's how you would design them, and that's how you would do it. But I mean, it depends. I mean, like, I've done them where there wasn't any void forms either.
And then you get like a little bit of bonus. It's like you kind of
The soil's there, right? But then stiffness attracts load, so really, you don't really want your structure to move more than half an inch. So if you move your building like half an inch, how much is that soil that you cast on top of really going to get?
I just wonder too, like backfill walls, foundation walls. I mean, when you design a building where you're properly burying,
Yeah.
you just say the load's dumped into the foundation, basically. You know, like on a smaller house, your load you don't like look at the global lateral pressures to like on your building to resist 40 kips of horizontal shear, right?
So in certain cases, you can actually get, like when an earthquake happens, right? The soils are actually moving.
Yeah.
So you can ask a geotech for the lateral earthquake pressure. So it's like, what is the soil going to be pushing on your foundation wall with?
Yeah.
And so a lot of times you should consider that. I mean, that's what, like passive soil is a kind of a measure of that to some level. It's, right, the resistance for your soil to actually push against. So if you like tried to have that wall push against the soil on the outside, right, how much does that soil resist it? And so you should consider it in some cases, right? You should look at it. Usually that pressure is pretty consistent with like an at-rest or an active earth pressure. And so you've already designed the wall for that pressure, so in an earthquake event, right, you might have already considered it. We're already done, and this is ridiculous. All right.
We made it. Couple
Fuck!
slides.
Seriously? All right, we are going to haul ass on Wednesday, okay?
We should just do the finish notes again or something. That would have been
Yeah.
Was it valuable? Was Helical Piers valuable?
It will.
No, kinda.
like it eventually.
No, I don't know either. Pile talk.